The binding of oxygen to hemoglobin within the erythrocytes is dependent on environmental variables within the bloodstream and the surrounding tissues. As we saw previously, we also know that the partial pressure of oxygen is a major driving force for promoting the diffusion of oxygen from the air in the alveoli into the blood, where it can then be picked up by hemoglobin. A hemoglobin saturation curve is a curve that visually shows the relationship between the partial pressure of oxygen and the binding or saturation of oxygen on hemoglobin molecules. Saturation is also referred to as SATs clinically and is stated as a percentage. Figure 22.26a shows us that the hemoglobin in the alveolar capillaries, where the partial pressure of oxygen in the alveoli is about 100 millimeters of mercury at sea level, is 100% saturated with oxygen, meaning that every single hemoglobin molecule is carrying its maximum of 4 molecules of oxygen. This is the maximum capacity of each hemoglobin molecule. At the tissues, which are using oxygen in their metabolic processes, where the partial pressure of oxygen, or PO2, is about 40 millimeters of mercury, the hemoglobin unloads some of its oxygen, where it will then diffuse from the bloodstream into the cells of the tissues that are using it. But it also shows us something interesting. Even though hemoglobin has unloaded some of its oxygen, it is still approximately 75% saturated, meaning that each hemoglobin has only unloaded 1 oxygen molecule and is still carrying 3 oxygen molecules. The oxygen hemoglobin saturation curve may also be referred to as the oxygen hemoglobin dissociation curve, as it plots where oxygen is unloaded or dissociates from the hemoglobin that's carrying it. The horizontal axis on the bottom of the graph gives us the partial pressure of oxygen in various places, with the lungs being shown on the bottom right and the tissues in the bottom middle. The vertical axes give us 2 pieces of information. The vertical axis on the left gives us the oxygen saturation of hemoglobin as a percent, with 100% being the maximum at the top left. The vertical axis on the right gives us the amount of oxygen in milliliters per 100 milliliters of blood. We see that in the graph itself, the oxygen hemoglobin saturation curve is S-shaped, which has some important physiological implications. The fact that the curve is broad at the top indicates that a large change in the partial pressure of oxygen translates to a relatively small change in oxygen saturation of the blood, and specifically the hemoglobin. The curve also tells us that at certain partial pressures, hemoglobin will unload its oxygen. The body needs to be able to use the oxygen, so if hemoglobin carries it and never lets go of it, other body cells and tissues would be unable to use it. Returning to the horizontal axis of the graph at the lungs, the partial pressure of oxygen entering the bloodstream is relatively high, around 100 millimeters of mercury. If we follow the vertical line up from the arrow, we see that the green oxygen hemoglobin saturation curve is around 100% saturation from the left vertical axis. At the tissues where the partial pressure of oxygen is about 40 millimeters of mercury, and we follow the arrow up until it makes contact with the oxygen hemoglobin saturation curve, we find that the curve has dropped a bit. Following the dashed vertical line, the graph tells us that at the tissues where the partial pressure of oxygen is lower, that hemoglobin has unloaded some of its oxygen, as it is now only about 75% saturated. The right vertical axis tells us that about 5 milliliters of oxygen per 100 milliliters of blood has been unloaded at the tissues. So what causes the phenomenon we saw in the graph, where hemoglobin unloads some of its oxygen at the tissues where it is needed? The metabolism of glucose at the tissues produces carbon dioxide, or CO2 gas. When CO2 dissolves in fluid, like the tissue fluid or blood plasma, it becomes acidic. The mild acidity of the environment at the tissues causes the bond between the oxygen and hemoglobin to weaken, and some of that oxygen is let go and is able to diffuse away from the hemoglobin and into the tissues where it is needed. The weakening of the oxygen-hemoglobin bond by acidic environments is called the Bohr effect, after Christian Bohr, who was a Danish physiologist. Acidic environments also have the effect of shifting the oxygen-hemoglobin saturation curve to the right, meaning that the oxygen-hemoglobin bond is further weakened and hemoglobin more easily releases its bound oxygen at a given partial pressure of oxygen. We'll examine this in the next slide. Figure 22.26b once again examines the oxygen hemoglobin saturation curve with percent saturation of hemoglobin on the vertical axis and the partial pressure of oxygen on the horizontal axis. The red oxygen hemoglobin saturation curve, which is the middle curve of the three, shows the curve at a typical blood pH of 7.4. The teal curve, which is the rightmost curve of the three, is representative of the curve at the tissues, where the pH is slightly lower at 7.2. Notice that at all partial pressures, the teal curve at pH 7.2 is always underneath the red curve, meaning that at more acidic pHs, hemoglobin is less saturated with oxygen, because acidic pH weakens the bond between the oxygen and hemoglobin. Typically, we find that the tissues have more acidic environments due to the production of carbon dioxide, which means physiologically that hemoglobin will release more of its bound oxygen so that it can be used by those tissues. Due to the fact that it releases more of its oxygen means it will be less saturated. This is an example of the Bohr effect. How is carbon dioxide transported within the bloodstream? Approximately 70% of the carbon dioxide is converted into a substance called bicarbonate. Within the erythrocytes is an enzyme called carbonic anhydrase, which functions to convert the CO2 into bicarbonate. And then bicarbonate is released into the blood plasma. Once the blood reaches the pulmonary capillaries, the reaction is reversed, where bicarbonate is converted back into CO2 and water. The carbon dioxide, being a gas, will diffuse out of the capillaries and into the air in the alveoli, where it will then be exhaled.